Hey guys, this is Mrs. Marquette, and today we're going to be talking about a new concept called imaginary numbers. Today is day 4 of our Solving Quadratics notes. So an imaginary unit, this I, is going to be defined as I is equal to the square root of -1. Okay, so that's our big definition for today. And it can be used to write the square root of any negative number. And that means that I squared is -1. So I want to motivate this a little bit. Like, why do we care that I is equal to the square root of -1? And really, what does that even mean? So I want to take you to this problem. X squared is equal to -4. So what that means is some number times itself has to be -4. So what we learned in our last lesson is that to undo that square, I can take a square root on both sides, and I would get x equals positive or negative something. And the issue here is that I don't know any numbers that have the property that a number times itself equals -4. Specifically because like 2 times 2 is 4 and -2 times -2 is also +4. So this is not a problem we've been able to solve in the past. We've kind of stopped here and said, okay, we can't take a square root of a negative number. That number doesn't exist. But what we want to think about is, okay, if it were just 4, like if I didn't have the negative, I could take a square root. So if I could take a square root, I would have a 2, but then I still have like this square root of -1 that I haven't dealt with. So what our I is going to do, our I is really just going to be like a tag for us to say, okay, if I could take a square root of a negative, it would just be this number. And the I just says, hey, remember that there was a negative under that square root. So this I is actually going to help us because it's going to make us able to solve any square root problem, whether it has a positive under the square root or a negative. So we're going to do all sorts of stuff with that square root of a negative number today. So here's our big property. If r is a positive real number, then if there is a negative under the square root, how I'm going to deal with it is just by tagging with an I, just saying, okay, that I says there was a negative under that square root. So if I have the square root of -5, I can really say, well, that's like the square root of 5, but I have to tag it with an I to say there was a negative. In the same way, we saw that I squared is -1. So if I squared this whole thing, if I said I squared and then my square root and my square will undo each other, I'll get I squared is -1, and then square root and square cancels, and I just get r. So we'll kind of see how that plays out later. But for now, we're going to talk about the fact that complex numbers might have a real part and an imaginary part. So real parts are just any numbers you know. It's like 2, -7, 0.23, 1/2. Even pi is a real number because I can write it down. It's a number that we can put on a number line. So those are all real numbers. They don't have an I. Numbers that are pure imaginary only have an I part. So that's like -I, +2i, 3i, -4i. Anything that has just a number part, even 1/2, but it has to have an I. And then imaginary numbers are just the real part and the imaginary part put together. So 2 plus 4i is an example of an imaginary number because I have a real part and I have an imaginary part. Notice that this a and this b from above, the a and the b are both just numbers. Everything else, -5 plus 7i, 2 minus 3i. I've just got all of those real and imaginary pieces. So 1/2 minus a third I has a real part and an imaginary part. We usually list, just for convention, the real part first and the imaginary part second. So that's when you finish your answer, make sure that you put real and then imaginary. But the reason that we really want to use these numbers are for solving quadratic equations. That's what our chapter is all about. So number 1 says solve the quadratic equation. We are going to use the same method as last time. So we'll go PEMDAS backwards. I'm going to subtract 10 from both sides for number 1. I get 3x squared is equal to -36. I don't want to take a square root yet. I still have to divide by 3 on both sides. And I get x squared is equal to negative 12. Normally we'd say, oh, well, the square root of negative 12 doesn't exist. I've got to stop. But because of I, we can keep going. So the square and the square root cancel. I get x equals. Don't forget your positive and negative. This negative, I want to replace with an I. Okay, because I'm saying, okay, there was a negative under the square root. Let's tag it with an I. But then what I want to deal with is what the square root of 12 is, if it was just that number. So if we remember from last time, I get 4 and 3, 2 and 2. So I've got 2 times 2 times 3 under my square root. So my final answer is x equals the positive or negative I times 2 square root of 3. Or I can write this with the I on the back end. So 2 times the square root of 3 and then times I. Usually this is how you will see it, with the I kind of at the back. But remember that we can write multiplication in any order. So 2 times square root of 3 times I really is the same thing as I times 2 times the square root of 3. So number 2 is exactly like it. I'm going to subtract 26 this time. And I'll get 2x squared is equal to negative 36. Remember to divide next. X squared is equal to negative 18. And since we know I, we can take a square root on both sides. Square root and squares cancel. And what I'm left with is x is equal to the positive or negative. This negative under the square root becomes an I, because what I really want to think about is what is the square root of 18? Because that's like a bigger thing for us to deal with. The I is really just a tag, like saying, hey, there was that negative, but we're not going to think about it right now. So square root of 18 is 9 and 2, 3 and 3. So 3 times 3 times 2. So I get x is equal to the positive or negative 3 square root of 2. And this time I'm just going to put my I at the end. Notice that this I, just how it's written, it has a little hook at the bottom and kind of a bigger dot on the top. That's how you want to write this I regularly. It tells us that it's the imaginary unit, that it equals the square root of negative 1. So we just all write it the same way. Everything else that we do with imaginary numbers is just going to be how do we add, subtract, multiply, and divide. So this is the big stuff, numbers 1 and 2. Everything else is what do we do with this I value. So let's look. Standard form is written a plus bi, meaning my real part is first, my I part is second. But we're going to treat this stuff just like adding like terms, so what we've done before. So number 3 says 4 minus I plus 3 plus 2i. Since there's a plus in the middle, it's like distributing a positive 1, so my signs won't change. I've got 3 plus 2i. And then combine your like terms. 4 and 3 is 7, negative I and positive 2i is plus 1i, which is the same as 7 plus I. So that's my final answer. That should seem super familiar from last chapter. If it doesn't, go back to the factor chapter and watch the video on adding and subtracting polynomials. Otherwise, the only difference with number 4 is remember that we've got this negative in the middle, meaning I have to distribute a negative 1 to both pieces. So I've got 7 minus 5i, and then negative 1 plus 5i. So combine your like terms. 7 and a negative 1 is 6. Negative 5 and positive 5 is plus 0i. But 0 times anything is just 0. So that just really means I have no I part. I have 0 i's. So my answer is just 6. Number 5, there's more of them going on, but I can still combine my like terms. Start with 6, and then I distribute the negative just to what has parentheses. So positive 2, negative 9i. And then if I have a positive, that doesn't change anything. So it's just negative 8 plus 4i. Combine all of your like terms. I have 6, 2, and negative 8 is actually 0. And then negative 9i and 4i is negative 5i. 0 I don't really need to write, so I can just write negative 5i. And that is my final answer. This time I have no real part, just an imaginary part. Why don't you guys actually go ahead and try number 6, see how that goes. One thing that I want you to double check and make sure you got on number 6 is that your real part is first and your imaginary part is second. So you should get -6 minus 7i. That's adding and subtracting. So again, combining like terms. If it doesn't look familiar, go back and watch the old video on adding and subtracting polynomials. The next thing is multiplying. And this is going to get just like a hair more complicated because, well, you'll see in a second with I squared. I need to distribute my 5i since I have a number outside of parentheses. So I get 5i times -2, and then plus 5i times I. And when I multiply, my 5 times my -2 is -10 with my I, and then plus 5, I times I, or I times itself, is really I squared. But we want to write this in standard form, meaning I have a real part and an imaginary part. So what I have to remember from way at the beginning is that I squared is equal to -1. So you should write that down on your notes right now. I squared is equal to -1. Because what that's going to do for us is we can replace that I squared with -1. So I'll get -10i plus 5 times -1, which is really just -5. Because 5 times -1 is -5. And then just for convention's sake, let's put the -5 first and the -10i second. Real part, then imaginary part, and we are all done. You don't have to put all of these steps, specifically if you don't need to write this step or this step. As you get more used to these problems, you probably won't need those steps. But that's a good thing to start with here. Number 8, when we had a binomial times a binomial, remember that we FOILed, or we multiplied our 7 times each piece and then our -4i times each piece. So I'll get 7 times -1, 7 times 2i, and then -4i times 1 is a positive 4i. -4i times 2i is -8, and then I times I is I squared. There's a couple things we can do here. First, I squared is -1. Hopefully you saw that. So that's right here. -8 times -1. Another thing we can see is that our middle two terms are like terms. So 14i and 4i adds to 18i, and then -7. So -8 times -1, that'll be a positive 8. -18i, positive 18i and -7. Combine your like terms and you get 1 plus 18i as a final answer. You guys should also do numbers 9 and 10. Please specifically do not skip number 9. I'm going to talk about it. Double checking our answers, number 9, the big thing to notice is that everything that has i's actually cancels out. I get a -18i and a positive 18i, and then my I squared becomes a positive, or a -1, so -9 times -1 is positive 9. This should always happen when we have a pattern that looks like this. 6 plus 3i, 6 minus 3i. The only thing that is different here is our plus and our minus. So that's going to come into play a little bit later. That'll be important to us. Number 10, if you get to the point where you can do this few of steps, so you get 27 minus 3i squared, you notice that your I squared is going to be a -1, so -3 times -1 is positive 3. That's really the pattern that you'll see, is whenever you have an I squared, it's just going to change the sign of the number in front of it. So there's really just one more thing that we have to deal with as far as imaginary numbers go, and we're going to use conjugate pairs. So a complex conjugate is really just like number 9. When I have a plus bi, so a number plus another number times I, the complex conjugate is just that same set of numbers, so a and bi, with a different sign. So these two have different signs. So if I'm looking at 11 through 14, that's going to mean that 2 plus 3i, the complex conjugate, is 2 and 3i. The only thing that changes is there's a minus in the middle. See if you can do the next three. Double check your answers here. Notice that your numbers and your real part and your imaginary part are all the same on all of them. The only thing that's different is in the middle. So even on this one, I don't flip the original sign. I only flip positive to be a negative. If it's a negative and the original, the conjugate is, or the complex conjugate is the opposite, so it's positive. Negative becomes a positive. The reason that this is important is because when we work with fractions that have i's in the denominator, we don't like, if you recall, when we have a radical on the bottom. So last time what we had to do with this kind of a problem is multiply by rad 3 over rad 3. So we get 1 rad 3 over 3, since this is a pair. So we had no more radical in the denominator. So if you don't remember that, go back a day, remember that video, or look back at your notes. So why that matters to us today is because if I have like 3 over 2 plus I, remember that I is really the square root of -1. So I have a square root in the denominator. So I've got to deal with that. The way we're going to do that is by using complex conjugates. So I've got a couple steps. The first thing I'm going to do is I'm going to see what is the conjugate of the denominator. Then I'm going to use the conjugate to get rid of all of the i's in the denominator, which is just like we saw in number 9, using the conjugate. And then step 3 is simplifying that expression. So in practice, if I look at number 11, what I don't like right now is I don't like this I on the bottom. So how I get rid of it is, first of all, noting that the complex conjugate of 1 minus 2i is the same thing, 1 and 2i, with a plus in the middle. Okay. And I'm going to set it up so that this is multiplication. And when I multiply the denominators, I want all of the i's to cancel out. That's kind of my goal. But I know that whatever I multiply to the bottom of a fraction, I have to multiply to the top. And I can multiply the numerators as well. So I'll multiply the numerators. 5 times 1 is 5. 5 times 2i is 10i. 3i times 1 is 3i. And 3i times 2i is plus 6i squared. And we'll deal with that numerator later. On the bottom, we get 1 plus 2i, minus 2i, and then minus 4i squared. Nice thing about that is my 2i and my negative 2i cancel. And then we know that this I squared is actually -1. So negative 4i squared turns into just positive 4. So my new denominator is 1 plus 4, which is 5. On the top, I have 5 plus 13i, and then 6i squared. When I multiply 6 times a -1, because that's what I squared is, I'll get -6. So really, I can combine my 5 and -6 to get -1 plus 13i all over 5. And that is a good, correct answer. How you will usually see this on an answer for a test is -1 over 5 plus 13 over 5i, just because we want to see a real part and then an imaginary part kind of separated out. But really all I'm doing is I'm saying, okay, take 5 and divide each piece by that 5. I'm going to skip to number 13. If I have just one number in the numerator, I can still identify the conjugate of the denominator, 2 plus 9i. It's just going to make my multiplication a little easier in the numerator. So I put 2 plus 9i in the numerator as well. The numerator is just going to be 3 times each piece. So I get 6 plus 27i. I get 4 plus 18i minus 18i, and then minus 81i squared. If you start to notice that your middle terms are always going to cancel out, you can get in the habit of just skipping those. That's fine with me. But I'll end up getting 6 plus 27i, and then 4 negative 81i squared is going to equal positive 81. So 4 plus 81 is 85. You'll see this as an answer on a test is 6 over 85 plus 27 over 85 times I. But those two answers are exactly the same. So I'll take either if it's a free response portion. I'm going to do one more with you, number 15. And then I'll let you guys do the last 3. So first step, again, is multiply by the conjugate of the denominator. So I've got 3 and 4i with a negative in between. And then the numerator I can distribute. I'll get 9i minus 12i times I is I squared. And then in the denominator, I'm going to get 9. And then remember that my outsides and my insides are going to cancel. So I'm going to skip writing that. And then negative 16i squared. Or if I think, okay, I squared is really negative 1, that's going to turn into 9 plus 16. So on the top, negative 12i squared is going to be a positive 12. So I get 12 plus 9i over 25. So I get 12 over 25 plus 9 over 25i. If you don't like that skipping steps, please write all of the steps that you need. I just want to show you that if you see those patterns, if you start to get pretty quick at these problems, you can make it a little bit shorter for yourself by thinking ahead a step or two and recognizing those patterns. You guys try 12, 14, and 16. I will put a little bit of time on the video and then I'll show you the answers. And that is what your completed notes should look like. So if you didn't get those answers for 12, 14, or 16, double check your work. I did work out the full work on 12 and 14, so see what makes sense, and then you can try your practice problems. Please come and see me if you've got any questions.